Professor Kaushik Jayaram. He got his PhD from UC Berkeley. After that, he went to Harvard to do a postdoc there. When he was doing his PhD, he did very exciting work on cockroaches, showing how cockroaches can go through very tight spaces. After he joined Harvard for his postdoc, he worked on the hammer robot, which is a legged robot, and he showed how he can optimize the robot gait such that the robot climbing speed and running speed will improve quite significantly. So now he's at CU Boulder. He's now leading his own group. What I heard a couple of years back is that he's now looking at new biological examples for inspiration. For example, spiders, and recently I also know that he started to work on vacuum wing systems, thinking about how resilient those biological systems are. So with that, I'm very pleased to have Kaushik, and Kaushik, that's all yours.
Thank you, Kevin, for the lovely introduction. And yeah, so first of all, I want to thank all the organizers for having me here and also giving me the honor of being the last speaker for the day. And so thanks to all of you for sticking it out. I know this is the first day of the conference, and so everybody's tired. So I'll try to show relatively less data and lots of videos and pictures. So hopefully. All right, so I'm going to talk about some of the work, what we're doing in my lab. We've seen a number of excellent examples today of bio-inspired robotics, and the different groups have talked about the different challenges they have. And when we think bio-inspired robotics, one of the first imageries which come to my head are the series of, or the suite of robots in Boston Dynamics. So here's shown from a couple of years ago that different kinds of bio-inspired robots. And now you have a lot more. And these robots are clearly amazing at what they do. So they're capable of amazing performance. They almost seem human-like, and they're being more and more integrated into different aspects of society. One thing I would point out is when you look at a lot of these videos, they are still in kind of what I would say, kind of well-defined controlled environments. So these could be lab settings, factory settings, and so on. And even these amazing robots, when you put them outside, they're still relatively fragile. So here's an example of one of the earlier versions of the robots, which gets caught under natural terrains. And again, this is from the Doppler challenge a couple of years ago. The same robot, while trying to go over uneven terrain, fails and is unable to recover. In contrast, animal systems are extremely robust. And by that, I mean they perform really well in uncertain environments. Here's a hummingbird kind of flying in the rain. Here's a baby goat running down the side of a cliff. Animals are also capable of handling unexpected perturbations. As you can see in this video, there's a hawk kind of flying through this cluttered terrain, trying to grab a squirrel. It misses him on the first time. The squirrel tries to escape, but you'll see that the hawk kind of manages to grab it in a second. Another example here, you see Jaboer kind of hopping around, and in the background, if you notice, there's a rattlesnake waiting to catch it, and right at the last instant, the Jaboer is able to make an escape miraculously. And finally, animal systems are also capable of working with unreliable components. And so here's Fate the dog, which was an opera a few years ago, and she's the happiest puppy, and she's hopping around like a little kid. The last example I'm going to show you is a fiddler crab. It got into a fight, got its arm hurt, decided it's better to just snap it off and run around instead of like carrying an injured creature. So these are just a small subset of examples what we see in nature. And when we think about this, what are potentially features which define the behavior of animals or the robust behavior of animals? A variety of like these keywords come to my head. So things like adaptable, multifunctional, redundant, repair, fault tolerant, and so on and so forth. And we've seen through the course of the day, many different groups have highlighted as a part of their own work, how they're trying to like bring these challenges or try to like account for these challenges. So just to kind of summarize, I still think as a community for bio-inspired robotics, one of the open challenges is still thinking about robustness and potentially how do we build that into systems? And by robustness, I'm going to broadly define it as maintaining performance in the face of perturbations. And so what my lab has been trying to think about is trying to build robust bio-inspired robots that can leave lab environments and operate effectively in natural conditions. And so the approach what we use in order to get that is basically this whole loop where we start by the behavior of interest. So we try to study animals. We collect a lot of data related to the locomotion biomechanics. We use this data to generate hypotheses about what the animals might be doing. We combine that with physics-based models to generate some simple kind of design guidelines, which ultimately feeds into the robot fabrication. And these robots can not only have new capabilities, but also serve to perform as like high fidelity platforms to understand biology better. And I'm going to walk you through an example as to like how we do this in a group. And so one of the behaviors that we're interested in is confined space locomotion. We know that cockroaches are excellent at getting through really small gaps. This is one of the annoying things about them, which is why many of us hate them. So what we did is we were like, okay, we challenged the animal, try to understand what kind of gaps they get into and what performance do they have. And so here's an example of kind of like the cockroach being confined. It's real time slowed down 20 times. Cockroach, just for scale, it's about 15 millimeters tall. When you have gaps of 12 millimeters, you can see the cockroach bump its head back and forth as it's trying to run. And the smallest gap we were able to get the cockroach to go was just 4 millimeters. And so, mind you, 4 millimeters is already compressing the body by over a third. And the speed at which it's going is about 5 body lengths a second. So put that in context. So Usain Bolt, when he ran his world record, was about 5 meters a second, 5 body lengths a second. So these animals can do this when they're squished to by over a third. And we did more experiments. We were like, okay, when you're squished, how much forces do you experience? And I'll tell you that no animals were harmed in the study. We tested that. We actually ran them before and after, and they were fine. And so what we see is this, I'm part biologist, part mechanical. So what we see through these measurements is like, as you squish the animal, the forces and experience increase with the amount of compression, but they're also nonlinear. So not only that the force increase as a function of compression, they also increase with the speed of compression. So this is for a materials person or classical mechanics, it's what we think of as viscoelastic kind of behavior. And what is really interesting is at these smallest gap sizes, these animals can be experiencing more than 800 to 900 times their body weight, and they don't squish. In fact, they run really fast. So these were all the experiments we did on the biology side. We collected a lot of data, and this gave us some insight into like what might be happening with the insect exoskeleton. And so then we went on to basically put these data together. We built a very simple physics-based model. So one of the unique things of going through confined spaces is that unlike typical legged locomotion, where you're just dealing with contact forces on the ground, you have also a drag force on your body and in your belly. And your thrust, which is also friction dominated, needs to somehow be balanced against the two. And so we built a simple physics-based model, and we were able to kind of make predictions as to what happens depending on the level of compression and what kind of speeds you reach. And based on this model, what we saw is that we get, if you are basically changing the friction on the ground, at really low ground frictions, you have no traction on your ground surface, so you can't really get anywhere, so you're really slow. However, on the other extreme, if there's a lot of friction on the ground, that also means that there's a lot of drag on your body, which means, again, you're not able to go really fast. So there is a happy medium in between where animals seem to do really well, and this is closely supported by experimental data. And so using this model, we were able to not only predict velocity of locomotion, but also stride length and amount of slip, what we can get. And this offered us key insights into thinking about like the design of the system. So kind of what kind of friction properties we wanted, what kind of compression, what kind of forces the robot needed to have. And we use this idea to kind of build our insect exoskeleton inspired shell. which is basically a set of plates interconnected by flexible membranes. And we finally put the whole robot together. We call it CRAM, or Compliant Robot with Articulated Mechanisms. Here's this in action. So here's a cockroach going through the smallest gap what we'll be able to do. And it's doing this in real time. So this is in under a second, the cockroach is able to get into a gap which is as small as like the size of 2 stacked pennies. And kind of borrowing this idea, we built a robot CRAM. The robot does pretty well, not as good as a cockroach, but it can still squeeze itself to about 50%. So basically what I've shown you here is by looking at biological systems, we can think about one of the features of robust systems, that is adaptability, or the ability to kind of conform to your surroundings. And the mechanism for robustness in this case was the use of soft compliant exoskeleton. And the new capability we unlocked in this process was the ability to move through confined spaces really effectively. So in the next few slides, I'm going to show you some more examples from our group that we're able to apply the same kind of approach to a few different problems. So here's some unpublished work looking at fault tolerance in biological systems. So on the top, you see a cockroach, an intact cockroach running at full speed. You can take out different parts of the feet or an entire leg, or sometimes 3. And you can see that the cockroach still moves pretty effectively. And actually, if you play them side by side and place close attention to what the legs are doing, the remaining tripod legs, which is highlighted in those like red dots, what you see is with and without before intact and in the wake condition, the animal seems to be basically not changing anything about like how it's cycling the legs. It's moving the legs at the same frequency. It's not changing any pattern, but it's spending more time on the ground, which makes sense because you can apply its force more effectively. So what this seems to suggest is potentially there might be some redundancy in multi-legged robots, and this can be a feature which can help you still maintain performance. Another example, this is from my work as a postdoc. We're trying to look at how we can achieve stability by taking advantage of closed loop feedback. So here's a small robot hammer. As it's running, it goes into these like body resonance modes, which make it bounce all over the place. And so this is during open loop locomotion. However, if we use feedback from the actuators, we can actually close the loop on the leg trajectories and kind of overcome the body dynamics to get nice consistent motion. And finally, here's an example of how small animals are really robust damage resistance. So here's a cockroach. It's running into the wall. So this is what these animals do in order to make like horizontal to vertical transition. They have these amazing sensors, but they choose not to use it because colliding to object doesn't cost them anything, and effectively they can be about 10–20% faster. So this is the difference between life and death for these animals. And this is only possible because the cockroaches are so small. And again, like using this idea, we were able to build a robot, passive robot with absolutely no sensors on board, which is able to make this like horizontal to vertical transition. So by taking advantage of size, we're able to negotiate obstacles without the need for any kind of sensing or this kind of controls. And this is one of the key reasons why, if you look at like some of the work my group has done, we've been like going smaller and smaller systems. And the latest, this is already from a couple of years ago, is the robot which we presented at ICRA a couple of years ago, Hammer Junior, which is a smaller version of the Hammer series of robots. It has all the capabilities as its larger counterpart, but it's just like half the size smaller. And it's, however, this is great. I talked to you about how robust you can gain robustness by potentially making small, but the other challenge by making things small, as you notice with a lot of these systems, is that they still carry a wire. So autonomy becomes a challenge. And what do I mean by autonomy? So here's a plot from a review paper from a couple of years ago, where basically the authors were considering autonomy with respect to 3 parameters. So onboard sensing, onboard power, and onboard control. They're looking at a small subscale of robots. So basically robots in small grams, less than 10 grams, micro robots. And what you see on these two plots is most of the robots have an autonomy score of 0, basically, which means that they don't have any of the onboard power control, and you have like a few robots which have all of them which have an autonomy score of 3. So what I think is still today, like many of the small robots at the scale are still rely on external power sensing and control. And I think this is potentially a challenge for our community to kind of solve so that these robots can be effective and deployed in natural conditions. So kind of rephrasing the mission for my lab. So we're now focusing on trying to build high performance, robust and autonomous bio-inspired robots. In the next few slides, I'm going to show some really preliminary work as to how we're trying to get there. So here's a new robot which we're building in the lab. So Clary, compliant, legged, autonomous robotic insects. So this work is being done by my student Heike Boots. And what's unique about Clary is that it's compared to most robots at the scale, it's squishy laterally. So what that means is it has a soft compliant exoskeleton, which means it is adaptable, it can conform to your surroundings, and this can give it a really unique ability to go through cluttered terrains. For example, like this example. And so this work is inspired by some early biological work, what we've been doing with full spiders. So shown here is an uncompatible spider. As you start shrinking it, kind of constraining it laterally, you see the animal kind of moves its legs to different configurations so that it's still able to adapt. The mechanism, what we are adopting is not exactly the same. We are kind of like taking advantage of the body, but we're still reorganizing the relative position of the appendages to be able to like conform. And this work is being led by the students Kendall and Heike. Another unique property, what we are trying to build into this robot is the ability to be fault tolerant. In order to do that, we have broken down the entire robot into modules. So each of the 4 legs is a self-contained electromechanical system. And what we're hoping for is if one of the system suffers damage or it can still potentially recover and the rest will still be functioning without failure. And so let me tell you first about the mechanical design. So each leg has 2 actuators, so it's capable of swing. So it's going back and forth and like lifting it up and down. We use cycle 5-hour transmission, and we use laminar planar fabrication technology to make these the shell of the robot. And so here's shown the whole system popping up to fold. Some early results with our actuator fabrication. So we take advantage of a femtosecond laser system to basically process these smart materials or materials sensitive to temperature changes. And what we're able to see with some early results is that they perform at least as good as a model predictions. We have some improvements, which is the reason why we're seeing better than kind of model performances, but we're hoping to go back and revise the model to figure some of these things out. Once we plug these actuators into the robot, we're able to get some really nice actuations. So this is a video which my student just sent like a couple of hours ago, so you didn't have the data yet for this, but what it seems to suggest is we're able to get about 10 millimeters of swing deflection back and forth with these with the new kinematics. So that's like about like 3 times on each edge. So next I'm going to move on to tell you a little bit about our SLAC, which is our smart leg actuation controller. So this is basically taking the electronics to power all those actuators. So essentially, it's a switching amplifier, which is capable of driving 2 piezoelectric actuators at a wide variety of frequencies. We can use generate different waveforms and provide a bunch of loads. nice thing about this is it takes advantage of some of the earlier work that I did, that we're able to do with content sensing and actuation and build it into this module so that we can do closed loop control of actuators. Again, here's some early results showing that we can generate a bunch of different waveforms. Here's just running the leg module using square wave. The same thing can be used to flap a wing, very different actuators, different loads, but it's still able to use the same kind of drive system for all of this. What's some ongoing work is basically building the power drive on the main system. So this is basically a DC boost stage, which is building up some work from Farrell and others. So once we have the main power coming from the central board, all the central board does is gives it higher level commands in terms of like what the light must be doing, and everything else is handled downstream by this lab module. And so the same kind of concept goes right, so that this way we have a distributed decentralized architecture, which we believe will make the robotic system more robust to any kind of external damage. And hopefully with these developments, we're getting closer to the power and sensing autonomy. And finally, I want to talk about how we're actually controlling these robots. So we're using a geometric framework to control these robots. So geometric mechanics has a wonderful set of tools for shape-changing systems. And the basic premise is that if there's a change in shape, then under quasi-static conditions, you can relate that to the motion of the robot. And so essentially shown here as a 3D system, you can represent all the geometric constraints as a vector field. And by taking the curl of the vector field, you can actually generate what are called as height functions. You can use these to generate optimal gates depending on the different criteria you want. For example, the maximum displacement, maximum efficiency, and so on and so forth. And it turns out for like the locomotion in particular, if you make some assumptions about ground contact because of the hybrid dynamics, you can actually simplify that even further. And so these 2D kind of height function maps, what you're seeing, basically boil down to simple lookup tables, which you can be stored on board a microcontroller, for example, and we can do onboard gate generation and optimization. And so this is some work done by student Hari. This is also in collaboration with the Ross Hatton's group at Oregon State University, and we're really excited to do that. So some early kind of results. Here's an example of like what we can do. So on the left, you see the system in body coordinate systems, on the right in the global coordinates. And essentially what's happening is, so the black lines are the passive legs and the red legs are the active ones. So you see the body rotating. Here's an example of a forward gate. So as the two legs are pinned to the ground, you see that there's a shape change which accompanies locomotion. So we're hoping to take advantage of this as we start doing gate planning and motion through motor drawings. So where are we at? So finally with Clary, so that's the actual robot. It comes in at about 3.2 grams with about 1.4 grams of electronics on board. It's about 4 centimeters in the largest body length. And it's a quadrupedal robot which can operate at a variety of frequencies. Right now, my students are trying to fix this. I heard that we're able to get the robot to walk and run, but as of yesterday, was able to pick up the place. So you still see some wires. So this is mostly to provide high voltage, but we are working on cutting the cord very soon. So to summarize, what does it look for a group? We are going to be working on improving autonomy and robustness, specifically on the autonomy side. We are building an onboard high voltage controller. We're calling it the micro havoc engine. We are also adding extroception. So this is some work done in collaboration with Jean-Michel's group, trying to like add cockroach-like antennae to like get information from the surroundings. We're also, again, making it smaller so that it can be more effective to collisions. And we're adding actual feet so that it can like cling to different surfaces, do multi-terrain locomotion. And so with that, I want to thank all my collaborators, my students, funding sources, and our partners. while you enjoy video of our spider walking, I'll take any questions.
Right. Are there any questions? Can I use the microphone after?
Thank you. Wait, can you answer the question that was asked to me about what micro robots are being used for?
Oh, I have a slide about that. Our hope is that we can address some pressing societal needs using robots, micro robots in general. So one of the areas is search and rescue, which Kevin alluded to, and a couple of others as well. Now that small robots can cling to multiple different kinds of surfaces, some work that we've done in the past is for like high value asset inspection. So this was a project done with Rolls-Royce where we're trying to like basically inspect jet engines as part of like the wood lab. One of the things I'm really excited about is if we can actually build them in swarms, deploy them as these collective intelligence systems. So we can do potentially a lot of like environmental monitoring with applications to agriculture, like air quality and so on. Especially me being in Colorado, it's really good to know when fires are coming. That's an application, and my vision in the really long term, I think Metin showed some amazing work this morning, but thinking about healthcare. So we're still some ways away from shrinking these robots, but if we can make them small enough and safe enough and biodigestible without lead and things like that, we can one day put them in the body. And so that's my vision. So some potential areas. Any other questions?
I wanted to ask, I just read that picture of the articulation. I didn't catch is it the shell that is collapsing, or is there an infrastructure that also collapses? And then I'll ask another question.
Yeah, so the shell is, there's infrastructure under the shell. So all the electronics and some of the mechanisms which enable your robot to sit, right? So that's inside. So as the shell collapses, the leg kind of like folds out. So you see L-shaped legs that are going from running on the feet, running on the elbows. And so that's what we're trying to optimize space. I stuffed all the useless components kind of under the shell and kind of squished it out.
Okay, I don't have another question to answer. Thank you.
Thanks.
Great talk. So Clary looks like an awesome robot. I have such a tension with building compliance into these small scale robots and whether that's useful at that scale, how limit inertia scale with actuation capabilities, et cetera, compared to larger scale robots.
Yeah.
Do you have any thoughts on that?
Yeah, no, I think that's a great question. So compliance is a challenge, and specifically at this scale, I think when we think about compliance and larger systems, so like legged running systems at large scale, they use compliance more as to like smoothen out ground interactions, and so basically preventing motor from burning out and stalling. So at these scales, we don't have those issues, but one of the things what we're trying to do is we're trying to navigate cluttered terrain and just squeeze through cluttered terrain. So I think like the only way to kind of think about that is if your robot is compliant, so then like geometrically it can adapt. And so I think that's the main focus of this work really, but like going forward, I think we are interested in coordinating things. Like there's been really interesting stuff done on the biology side in terms of coordinating limbs with like your back, and Dan Coleman's group is doing interesting work as well. So I think it's still helpful if you're trying to go through small confined environments. There is potentially, and so I'm thinking about compliance more in the sense of shape changing, but less so in terms of dynamics, which may be something you're alluding to. So in terms of the dynamics and mechanics side,
That makes total sense. Yeah. squeezing in spaces versus bouncing off.
Yeah.
Just a concern for that the shell functions. Are there any mechanical functions of the shell? Are you using it as a single door mechanism to control the configuration of the legs or protection? Another question is the biological system of a cockroach. What are the functions of the shell when they are swimming through the barrel confined these
Yeah. So what are the functions of the shell? Both in biology and in the robot. I thought I had a slide, but I don't. So on the robotics side, a shell is basically used as a transmission in this case to do like conformation change. So depending on the external force, you change the geometry. So I think that's the function of the shell right now. There's some other subtle functions in terms of it can hold the different segments together, but that's more of an engineering challenge. But in the biological system, I think the shell does many things. I think it's the shell is a part of the exoskeleton, so it's binding all the fluid inside, keeping all the organs intact. It has sensors on there, so it's getting a ton of information about what the environment is doing. Animals breathe through the shell. So in terms of biological functions, there's a lot of those things. But there are features which people have shown, depending on the different animals you look at. They have like ridges and things, so which provide anisotropic friction, for example, similar to a pathway. So what I have observed is that unless you really push a cockroach to an extreme, they can't do a reverse turn. So they can't like go back. They always try to like turn. And part of that is because the shell, the way it's oriented, they have differential friction in the back. So it's easy for them to go one way and not back up. So mechanically, those are some interesting things with the shell, but depending on the organism, they
All right, so for the interest of time, I would say let's end here. Thank you again, Kaushik. Thank you for coming today. I think this is the end of the workshop. We look forward to seeing you in events tomorrow, Wednesday, and Thursday. Yeah. And some of the videos will be uploaded to the workshop page.
Thanks for inviting me here.
Yeah, it's great to see you. Yeah. If you have time next time.
Yeah, man, sure.
Yeah.
Anytime, really, especially in summer.
Yeah. Like the last thing is if you remember, press air power.
Yes.
Is there a point of doing that, or should we? I mean, we have some good data pictures.
I know. I mean, we'd love to. Just I'm not sure. Yeah, we don't need to. We don't.
I think, yeah, even this the turn on data and pictures, I think usually
Yeah,
there's interest.
I'm not sure if you knew, but Cam had to take a break for like a year and a half. He's back in like full force. So I really would like to actually.
Sure. There's no pressure.
No, it's fine. He's fine now. So let's do it. That's
We're
great.
gonna end this meeting, right?
Yeah, I need to go catch a flight.
Okay.
Oh, okay.
Bye, it
Okay.
was lovely seeing
See
you.
ya.
Thank you.